Welcome to the next part of the tutorial. In this part, we want to talk about blockchain confidentiality. To motivate blockchain confidentiality, we consider supply chain management as an application. In supply chain management, we have different enterprises, different participants like middleman, supplier, carrier, manufacturer, bulk buyer. These participants, they want to work with each other, but they don't trust each other. And as a result, they don't want to share their data with each other. So we need confidentiality here. We need confidentiality of data. And we have some global communication, some global transactions between these enterprises where these communication follow service level agreement, which is agreed upon by all participants. For example, the bulk buyer places order manufacturer places order with middleman. We have arrange shipment, we have delivery, we have big order, and we have all types of these global communication or like global transactions among these enterprises. However, each of these enterprises, each of these participants has its own local transactions as well. And the blockchain system needs to support both public or global as well as private or local transactions. So one solution is to say, okay, we replicate a single blockchain on every party, and then this blockchain maintains all private as well as public transactions, and it is replicated on every participant. However, it doesn't preserve the confidentiality of data because every party has access to all transactions of all participants. As I said, we need to maintain all public and private transactions. And if we replicate all private transactions on every party, then we cannot preserve confidentiality. And also, it has poor performance because for replicating every transaction, we need to run some type of consensus protocol. And for example, the manufacturer need to maintain private transactions, which are for example, supplier. And it results in poor performance because first of all, it needs to maintain transactions that are irrelevant to manufacturer, and second, it needs to be involved in consensus protocols for those transactions. Another solution is to say that okay, we can maintain like two blockchain ledgers on each party. A public blockchain ledger, which is basically this green ledger, which is replicated on every party and maintains these public transactions, and each party maintains its own blockchain ledger or even its own database. But the problem is data integrity because these transactions are related to each other. For example, the local transaction or the private transactions of manufacturer are based on this public transaction. Based on this place order, the manufacturer decides how to basically manufacture some product. So this is these two blockchains are like dependent to each other, and we have data integrity issue. So Caper is an example of a blockchain that tries to solve confidentiality. In Caper, the blockchain ledger is a DAG structured blockchain ledger. And the logical view of the blockchain ledger is as follows. We assume that we have 4 enterprises in different colors. So there are 3 different rules. First of all, there is a total order between transactions that are initiated by the same enterprise. So let's say the green enterprise initiated T11, T12-1, T13, T14, and T15. Or the blue one initiated this blue transaction as well as this one. So we have a total order among transactions that are initiated by the same enterprise. Second, we have a total order between global or public transactions. So this is a public transaction, T12-1, T23-2, and T34-3. As can be seen, these public transactions, the sequence number has 2 parts. One part shows the order among the transactions of the initiator enterprise. So this 12 shows the order among the transactions of the initiator enterprise, T11, T12, T13, T14, T15. And the second part shows the order among the public transactions or global transactions. So we have T1, T2, and T3. So there is a total order between them. And as can be seen, local transactions might use data that is coming from the global or public transactions. So T13 use data that is coming from here. So these arrows shows that T14 uses data that is coming from here. T15 uses data that is, or T42 is. And this left-hand side figure is the logical view. This is not maintained by any enterprise. Each enterprise maintains its own view of the logical view. So enterprise 1 maintains its own view that includes its local or its private transaction as well as all global transactions. Enterprise 2 maintains its local transaction as well as all these 3 global transactions. Similarly, enterprise 3 and enterprise 4. So each enterprise still maintains a DAG structure, basically ledger. So we need to run local and global consensus. Local consensus for those basically local transactions, which depends on the failure model of nodes. Crash-only failure, we can use Paxos. Byzantine failure, we can use PBFD. Global consensus needs for those 3 global transactions, white boxes. In Caper, there are 3 global consensus. One is using a separate set of orderers, one is a hierarchical global consensus, and one is a one-level or flattened global consensus. Using a separate set of orderers, let's assume that we have 4 different enterprises, alpha 1, alpha 2, alpha 3, alpha 4. Each of these lines is a node. So alpha 1 has 3 nodes, alpha 2 has 4 nodes, and so on. And we have a separate set of orderers, O1, O2, O3. This is kind of similar to what has been used in Hyperledger Fabric. So in Hyperledger Fabric, we have a separate set of orderers, right? So it is kind of similar. So we have a disjoint set of orderers, and they try to globally order cross-enterprise transactions. So when a request comes to the enterprise alpha 1, they first run their local consensus to ensure that nodes in alpha 1 in the enterprise alpha 1 agree with the order, and then they send the order request to the orderers. Then they run global consensus, and then they send a sync message to everyone, including this sequence number. These are basically those 2 sequence number in the ledger that I showed you, that T12, T1, that one was the global sequence number, one was the local sequence number. So they send this sync message to everyone and saying that, okay, this is a global transaction, so please append this to your blockchain ledger. So the orders approach comes with an extra cost of adding orders to the system. In the hierarchical global consensus, since enterprises do not trust each other, we run the Byzantine fault-tolerant protocol among these enterprises. And at each step of the Byzantine fault-tolerant protocol, we run the local protocol of each enterprise within the enterprise. So you see that in the first step, we have the proposed phase, and then they run Paxos within the enterprise alpha 1, we run PBFT within the enterprise alpha 2, and so on. And then we have the second phase, which is an N-square phase, and then Paxos, PBFT, and so on, and then commit phase. So in that way, we distinguish the trust at the node level and at the application level. So here, the application decides, all nodes together decides to vote for that particular message or not. And the third one is a one-level global consensus. So the hierarchical consensus requires an expensive two-level consensus protocol, because in each step of the global consensus, we need a local consensus within each enterprise. In one level, basically, we have a three-phase protocol where all nodes are going to talk to each other. And at each step, if we receive messages from 2/3 of enterprises, not all of enterprises, if we receive the message from 2/3 of enterprises, it's sufficient. And from each enterprise, we need to receive message from local majority of that enterprise. What is local majority? If the enterprise has 4 nodes, or let's say 3f plus 1 nodes, then we need message from 2f plus 1 nodes of them. If it has 2f plus 1 nodes, we need messages from f plus 1 of them. So we need message from local majority of 2/3 of basically enterprises, or let's say more than 2/3 of enterprises in the one level global. But note that here we have communication among all nodes. So we assume that enterprises know the nodes of other enterprises, whereas in the previous one, we assume that enterprises do not know what are the nodes of each other. So they just know that there is an enterprise, and we don't know what's happening within that enterprise. So this is like a trade-off. So another way to basically guarantee confidentiality is using Fabric and using different channels. So this is another view-based way to guarantee confidentiality. So in Fabric, we can use different channels. So saying that we have like 8 different like enterprises, or let's say different nodes, or we can interpret these nodes as different enterprises or different like single nodes within the same enterprise. And we want to preserve confidentiality. We don't want these 4 nodes to be aware of the data of these 4 nodes. So we can use channels. We can separate these 8 nodes into 2 different channels. So a channel is basically a private subset of communication between a set of specific nodes. So these nodes maintain the same data. These nodes maintain the same data. And they might still share the same set of orders, or might have different set of orders. And this channel has its own ledger. This channel has also its own ledger. And these orders know that, okay, if transactions are coming from this channel, they have put them in their own block, and from this put them into like the green block and the like red block. But here the problem is, if we have a cross-channel transaction, then the processing is challenging. And another way again to address confidentiality is using cryptographic techniques. So we can still have like the same blockchain ledger, maintain the same blockchain ledger on every node, but we can use like cryptographic techniques and basically encrypt some transaction, some private transaction. So this idea is used in Fabric and in private data collection. So within a single channel, we can have private and public data. So these two nodes can have private data, so have private like data collection. These nodes have also private data collection. So as can be seen, the ledger, they maintain the same ledgers. They still maintain the same ledger, but the ledger, we have like transactions that is like purple transaction, we have green transaction. This green transaction is hashed, so it can be seen only by N1 and N2. This pink or purple transaction is hashed, so it can be seen only by N3 and N4. So so there is still a single shared ledger between all nodes, but the ledger might include transactions that are hashed. The problem here is the cryptographic cost and basically the low performance, because all nodes need to maintain the ledger, the same ledger, and the ledger might include many private transactions that are irrelevant to the node. So this green node maintains like a transaction, this like T1 that is irrelevant to the node. So in this part, we talked about view-based techniques and cryptographic techniques. So in view-based techniques, the problem is managing these views and establishing consensus among all views. So whereas in cryptographic techniques, the cost of managing views is lower. However, in cryptographic techniques, we have overhead of maintaining transactions on irrelevant enterprises.